We saw earlier that we can achieve the rate 1 minus h delta for a binary symmetric channel. In this lecture, we will extend that proof to the case of general channels and show that we can achieve the rate max over input distributions, the mutual information between the input distribution and the output. In fact, the way to show this is show that for any input distribution px, we can achieve the rate I of pxw. Okay, so that's what we will show. So to do that, we'll build up on the proof that we had for the binary symmetric channel. Recall that for binary symmetric channel, our scheme had the following structure. So we generated this random code words x1 to xm. These were all vectors of length n because we were interested in n length codes. And what we did was that for each m, we checked if the received vector y and the code word xm, if we check that if their Hamming distance is less than rho or not. So we can view it as checking if, say, so this is what we checked. This for every m in 1 to m, and if we found one unique m for which this holds, then we decoded that m. Otherwise, we declared an error. So one way we can visualize the structure of this decoder is as follows. We can have this sets acceptance regions A1, A2, one corresponding to each message, A capital M, and you have this received sequence yn. Use a different color, and the received sequence yn basically goes, we run all these tests, and these tests check if yn belongs to this set, this set, this set. So you get a yes no answer out of it. So these are these bits b1. So this bit b1 is bm. So here the bit bm is indicate a function yn belongs to am. Okay, and so you get all these bits, and then this decision maker, it does something here. It looks at all the bits and declares the message m if bm equals to 1 for if bm prime equals to 1 only for m prime equal to m and for nothing else. So if only for m prime equal to m. Okay, that was our decoding structure, and therefore error can happen if there are more than one. If there, so when can error happen? And error can happen if when m is sent, bm is not equal to 1, or b prime equals to 1 for some m prime not equal to 1. Okay, these are the two cases in which error can happen. Then this using union bound, we saw that the average probability of error, the expected average probability of error corresponding to this randomly chosen code words x1 to xm can be bounded by, they were all generated from the same distribution Pxn, can be bounded by Px and Yn. So we had this first part where dh of y and xm was greater than rho. So that is basically if this was a binary symmetric channel, or under m minus 1 times. So this is for one of these other m prime showing 1. Probability under the independent distribution dh. Okay. So in fact, we can see that this is a very generic setup. If you are given any set a1 to am, in fact, if you're given any set A, here the set A is the set of xy such that dh of xy is less than equal to rho. For any set A, we can define the set am. It's the set of those y for which xm, the randomly generated xm, and the randomly generated xm and y belong to A. Okay. So this is a special case of this more general looking rule, which can be defined for any set A. We have chosen the set A to be this one, the one where the Hamming distance between the pairs of sequences is smaller than rho. So in this notation, what we can see is that the expected probability of error is less than equal to, okay, this is already this is the same thing I'm writing with by bringing in this set notation. And this is A. Okay. So that's the bound we saw for the binary symmetric channel, and we can roughly, the analysis was generic. We will see, we'll formalize this part soon below. But roughly it was generic, and it can be expressed in terms of this set A, and then you can define AM using the random code book. It's the set of those y for which xm comma y belong to A. So now if you stare at this expression, it looks like this set A is sort of the acceptance region for the hypothesis testing problem of P xn yn as the null hypothesis and the independent distribution with the same marginals as the alternative hypothesis. So A is the acceptance region for H0, the set of sequences xy where you declare H0. Okay. And this probability here, it's the probability that it was indeed the joint distribution H0, but you declared the independent distribution. So this is the probability of false alarm for this hypothesis testing problem. And this probability here, this one here, this is the probability, this is the probability that the hypothesis was H1 but you declare H0. This is the probability of missed detection. Okay. So in general, we will see that this is the right view to have. In fact, you can take any test for this problem and construct a channel code using this recipe. And that's what we will do in our achievability scheme. In fact, we know what is a good test for this. This is a set of those sequence pairs for which the likelihood ratio of coming under the joint distribution versus independent distribution is more than a threshold lambda. All right. So this is what we will do now. We'll give a single shot scheme. So we can use this heuristic to design a single shot scheme. So what is a single shot scheme? Here in this, the way I have put the scheme down, I had to use the fact that n is large, and that's when this concentrates around n delta. The distance concentrates around n delta. But with this view, I don't have to think of a large n. I can come up with a single shot scheme which I can instantiate for multiple copies of channel to get the result that we want. So here is the formal theorem that we can prove. Okay, so consider a channel W from X to some Y. Okay, and a distribution on the input. Let y be the distribution of y given x be given by w. So y is the output when w is input. Now suppose, so now you have a joint distribution pxy where the conditional distribution is w and input distribution is px. So suppose under this joint distribution, make some space. The probability that xy appears by the way, this condition and this entire approach, this is sort of the acceptance region for a test, something we saw when we proved Stein's lemma in one of the early lectures. So suppose this condition holds, okay, then we can find x1 to xm. Okay, so we can find x1 to xm with m equal to, so epsilon is some factor, but lambda is important here, such that so we can find this, sorry, and a mapping D from y to 1 to m such that 1 by m summation m equal to 1 to m probability under xy that d of y equals to m under y given x. Just w. Okay. What's that? Summation over y such that you decode y as m. This is just single shot, so yn now looks like y, and you observe this y when the input is xm. Okay, so this is the average probability of correctness. Okay. This probability is greater than 1 minus 2 epsilon. So you can find a code with average probability of error less than 2 epsilon. This epsilon, this is 2 epsilon here, and this is another epsilon which adds up from this. So that's the claim. Okay, So this is, you can think of it as a single single shot as in, because we are not doing it for IID sequences, single shot achievability result. Okay, so before I prove this, let's see what we can do with this. So now, to be able to find a code of a given size, we just have to find this appropriate lambda. So corollary, let's just do that corollary. For any input and distribution to be able to see this theorem, for any input distribution Px, Ipx W is an a 2 epsilon achievable rate. Okay. So how do we show this? We will just use this result here. So for us, let's say W is replaced. So we apply the theorem above with n copies of W in place of W, and the IID distribution Px in place of Px. So this was a single shot result. It asks for a Px and it asks for a W, but we now have n copies of both, and we apply this. But we have to choose a lambda. So now, what is the lambda? So if the input distribution is independent and the channel is memoryless, as we have, then you note that this distribution itself is independent, and therefore this log of independent distribution becomes sum t equal to 1 to n log of px xi yi. So this is the sum of IID random variables, and therefore it concentrates around its expected value. So with lambda equals to n times the expected value of log pxy expectation is with respect to this independent measure, the joint measure, because that's what the probability outside here is, log of xy. So here the random variables are this x and y by yeah. Okay, so this guy, we want a large probability lower bound, so let's back off a little bit. How much do we need to back off? Well, we know this is just square root n times some variance of this random variable divided by epsilon. Okay, so then this condition holds. Let me call it this condition here. So by Chebyshev's inequality hash holds for this choice of lambda. Okay, so right, so we get something like this, and therefore we can find a code in the code of length n, and size. Okay, so what is the size of the code? Size greater than, so this is epsilon size greater than epsilon, now lambda 2 to the power lambda is 2 to the power n times this quantity, right? By the way, what is this quantity? The first term here, that's very important. So this quantity here, the first term is exactly equal to the mutual information between x and y, and minus something which is some c times square root n. So you can find this is why we had this log likelihood ratio, because its expected value is mutual information. Right. So n times I xy minus c times root n with average probability of error less than 2 epsilon. Okay, and with this so you have rate greater than ixy minus something small implies ixy. So if size is this, what is the rate of the code? So rate is greater than, so we divide this by n, so ixy minus c by root n and minus 1 by n log 1 by epsilon. Okay, so in the limit as n goes to infinity, this ixy becomes an achievable rate, and that's the proof. So this is very good. So we had a single shot result and it gives you the scheme. So if this is true, this would have implied, this corollary implies that channel capacity must exceed ixy for any input distribution px, and therefore it exceeds the max over px of this. So we have shown this part. Okay, so that's the corollary. But so what's the main result? The main result we are claiming is this one here, that the if you have given this channel, then if you consider this lambda which satisfies this condition, then you can attain the rate, or you have a code of size epsilon times 2 to the power lambda. This is a single shot result which gives a desired n shot rate result. So how do we show this? The proof is very similar to what we did for binary hypothesis test, for binary symmetric channel. Okay. So let me give the proof here. So let A be this set. A be this set, this one here. So this is the set of xy such that the log likelihood ratio pxy okay, so that's my set A, and what we know is that pxy of A is greater than equal to 1 minus epsilon. In fact, as we had seen earlier in analyzing hypothesis testing problems, pxy of A is equal to summation over xy in A px py of xy. So now we multiply and divide by pxy. These calculations we have done earlier. This is the same. The set is of the same kind that we had seen earlier in proof of Stein's theorem. Into pxy. So note that over the set A, pxy by pxpy is greater than 2 to the power lambda. So this guy is less than less than 2 to the, so each of this ratio is less than 2 to the power minus lambda, and then you have this part summing some probability, so this is less than 2 to the power minus lambda, right? So okay, so consider this code book C, which has x1 to xm generated IID, so independently analytically distributed with probability distribution px. Okay, so we have the code book now. Now the decoding rule is as before. So uh, let d of y equals to m if xm comma a belongs to xm comma y belongs to a and m is unique such index. Okay, so for no other uh, index, this xm comma, sorry, let me just, this is the rule that we had before. If m is the unique index m prime such that y comma x m prime comma y belongs to a. And what if there is none or there are many, then you declare an error. Okay, so this is exactly the structure that we had here, this one here. So you declare this is an acceptance region and you declare this guy if both xm and y belong to this a. That's the structure we had. That's am here. Okay, this is our decoding rule. And following exactly the same calculation as what we had for the binary symmetric channel, the expected probability of error x1 to xm can be bounded. See it on this side. The expected probability of error x1 to xm can be bounded by two parts. First part is the probability that although m was sent, but the code word for m, this expectation, I'll just keep this expectation here. So the code word under w summation over y such that x, this is the random part in this expectation, xm comma y doesn't belong to a, and we look at probability of all such y given x. This is the first term, and the second term is again same average probability, but you find an m prime which is different from m such that and you get a y, you receive a y when xm is sent such that x m prime comma y belongs to a. Okay, so as we saw in the binary symmetric channel case, this thing doesn't depend on M at all, and this thing is exactly equal to Pxy of A complement. And this second term here again doesn't depend on M, and this is exactly equal to Px Py of A. Okay, that's something we saw earlier, and this can be shown again. So this probability of error here, this average probability of error, is less than equal to Pxy of A complement plus M minus 1 times so therefore if you so then what we've shown is that the expected probability of error is less than equal to Pxy of A complement plus M minus 1 times Px Py of A. Okay. But we already saw that this first term here, the way we constructed our set A, this is less than equal to epsilon plus M minus 1 times. I'll just upper bound it by M, that's convenient for us. M times 2 to the power minus lambda. And now if you choose M to be floor of epsilon 2 to the power lambda, which is less than equal to 2 epsilon, if M equals to all right. So the average probability of error is less than this, implies the expected average error is less than this, implies there exists x1 to xm for which PE of x1 to xm is less than 2 epsilon. Okay, and of course with and m is greater than epsilon 2 to the power minus lambda minus 1. So that's the proof. It's very interesting. So we were able to construct this from just this test, and this is very intuitive. The reason you can send any information over this channel is because this is not a useless channel, and therefore somehow we can relate the code construction to the test for whether this channel is useless or not. So now what is a useless channel? Useless channel is the one where this distribution is independent, and when this distribution is independent, then when channel input and output are independent, then nothing can be done. So if you give me the acceptance region for that test with false alarm probability less than epsilon, then we can bound the rate in terms of the error exponent of probability of error of type 2. Okay, you see that m times this probability of error of type 2 must be smaller than a small like a small number. That's the probability of error. Therefore, the rate of m is related to the error exponent of probability of error type 2. So heuristically, by Stein's lemma, the probability of error of type 2, given that the probability of error of type 1 is less than or equal to epsilon, for pxn yn versus pxn pyn, is the divergence between pxn yn by divergence between pxy and pxpy, which is exactly the mutual information. So this single shot proof and the next combined proof formalize this part. Okay. That's the idea. So to conclude, we were able to extend this scheme that we have for binary symmetric channel to a general channel. And in fact, we gave a single shot result. This is very powerful. This kind of result, it doesn't use so much. In fact, this can be extended easily to continuous channels as well. continuous alphabet channel as well. It need not be for discrete channel. All we need is a lower bound for this log likelihood ratio, and the same proof can be repeated after that. Okay. And this is the great single shot achievability scheme which works in this single shot format. And we can get very precise result about how things change with n as well. Right. For example, it was not a priori clear, but this rate is less than mutual information, not more than that. Especially when this is true for probability of error less than epsilon, for probability of error less than half. Okay, so that's a result. Capacity must exceed this. In the next lecture, we will provide a converse result showing that no code can beat this maximum. See you in the next lecture, which will be our final one for this unit 13 on channel coding. So see you next time.